All right, here we are again. Um, all right, so what are we doing today? So we actually had just one more little piece of business to attend to in chapter 9, and then we're ready for 10. Okay, so let's get that going. All right, let's get everything open. And by the way, first let's go to Moodle. Let's see if there's any surprises there for us today. Let's get that out of the way. All right, here we go. Oh, yes. Yeah, I'm glad you mentioned that. There will be a chapter 9 and 10 problem set. I haven't posted them just yet because I needed to make some changes to them, but they'll be ready very, very soon, like probably this afternoon. After we're done, I'll take care of it. So, yeah, now that you mention it, the calendar, we better look at this calendar. Because as you know, we're rapidly reaching the end of the course, which ends officially next Tuesday on the 19th. Oh, God. Of course, there's ads here. Come on. All right, here we go. So here's the calendar, and it's just annoying me to no end here. All right, let's pick a different one. How about this one? That looks like it should be very readable. Yeah, there you go. Or maybe that one. Okay, so today's Wednesday the 13th. We're meeting today, tomorrow, and then we've got next Monday and Tuesday, and that's it. So let's see, how should we do this? Now, you've already got on Moodle a chapter 8 problem set. Let's go take a look at it. And by the way, the second midterm is there. It's down here somewhere if you want to get started on it. And this one, I think we agreed, is due on Monday the 18th. More due dates. Here it is. Here it is. So there they are. So what we decided to do, which I think makes perfect sense, is to have the second midterm, the chapter 8, 9, and 10 problem sets due Monday night, midnight on 1/18, because of course the course ends on Tuesday, the 19th. And so yes, the chapter 9 and 10 problem sets, I just have to make a couple of changes to them, and then I'll have them up probably this afternoon. So you have plenty of time to work on them. And then, of course, the final exam, when we're done with chapter 10, which will probably be tomorrow. In fact, yeah, just to avoid running out of time, what I think I'd better do is I'm going to post the sample final, which again is based just on 8, 9, and 10, probably this afternoon. And when it's there, I think what we probably will have to do, just to be on the safe side, is that as soon as we're done with 10, which probably will be tomorrow, we should at least start looking at the sample final, and then we can go over it in full detail on Monday, and if necessary on Tuesday. All right, so for today, we'll just be looking at chapter 10, but it's fairly long and involved, so it'll probably spill over into Thursday, and then we can at least begin the process of looking at the sample final, which, remember, it goes to 8, 9, and 10, so it's a long one. So that way we won't run out of time on Monday and or Tuesday. So that we have to take care of that first. Then the other thing too is the school always likes me to announce that the evaluations are available. I think they started sending them out or making them available yesterday. And the thing is, the school wants to see them, and I can't make you do them, but I would just like to encourage you to do them, because, the school wants to know what's going on in the courses. And, if you've got a few minutes, maybe you could take a look at it. I don't know how long it takes. I remember the one we used to do in the classroom was fairly short. There's a bunch of fill-ins on the front, and then on the back there was room to write comments. I think in the online version, you also have the ability to do the same thing. You can write your scores, but you also have room to write comments. And you might not think so, but they actually do read the comments. It doesn't just disappear into the bureaucracy. They really do look at them, and especially if you have ideas for how to make the course better, that would always be very welcome, because we're trying to cram in a 16-week course in 4 weeks, and sometimes issues can arise. So just when you get a chance, try to remember to take a look at those evaluations and send them in. You'll only have until midnight on the 19th to send them in. If you forget after that, you will not have an opportunity to fill them in. So it's really just over the next week or so that you can fill them in. All right, what else do we need to go over? I think that's about it. So, and also, of course, don't forget, if your first midterm hasn't been handed in yet, you can have until midnight tonight, and then I'll do all the corrections, and then we'll start with the next batch. Okay, so right now we have one last detail to consider in chapter 9, and then we can dive into 10. All right, so of course 9 is our discussion about confidence intervals. We mainly focused on confidence intervals for the population mean, but we then at the end introduced confidence intervals for the population proportion in the appendix. Okay, but there was one more case that we still haven't had time to look at. All right, let's get that open. And what would that be? Well, this is what we did yesterday. This is the formula for calculating the confidence interval for the population proportion. And we did this in 2 different ways. We did it algebraically, and we did it with our calculator's built-in functionality. We also noted that with the proportions, we only use the normal distribution. As soon as you see that this question involves calculating a confidence interval for proportions, you automatically know to use the standard normal distribution. Okay, so there's no decision that needs to be made. The rest of it is pretty similar. If you look at this formula again, you'll see that we have, of course, a point estimate. Okay, this plays the role of X bar when we're estimating confidence intervals for the population mean. This time, what we're trying to estimate is the population proportion. And then, of course, the second term is our margin of error. Now, every different situation, when it comes to confidence intervals, what separates one from another is always that margin of error. This is what's different. But if you notice, this one component of it never changes. We always need to draw a critical value, as it's called. In this case, we call it a z-score, from some probability distribution, typically the z or the t, but not always. And that part never changes. All right. So we're looking for a z-score, or in the case of the population mean, sometimes the t-score, and then that is attached to some value over here. And by the way, this, I didn't mention this before, but this piece in the square root sign is called the standard error of P. Okay, so collectively, those two create our margin of error. And then once we have all the information, we can easily construct our confidence intervals. And what separates the different confidence levels, 90%, 95%, and 99%, is the z-score. Okay, these other numbers never change. So it's the z-score that changes when we change the confidence level. And the result of that is that as we keep increasing the confidence level, as we've seen, as we look at the summary at the end, the higher the confidence level, the wider the interval will have to be. Okay, no exceptions, because each time we increase the confidence level, the z-score goes up. And that's why this is happening, because we're looking at a larger and larger percentage of the standard normal distribution. Now, down here somewhere, yes, here it is. We introduced the steps you need to calculate these intervals on the Texas Instruments calculators. And here we need to note that, of course, we're going to the stat test menu. This is where all the confidence intervals are. But because there's never going to be a t-distribution involved, here the choice is very obvious. It's one prop z interval. In other words, one proportion z interval. Z for standard normal, int for interval. Once you've chosen that, you only need basically two things, x and n, okay? So x is the number of people in the sample with a specific characteristic, and n is the sample size. Actually, x doesn't have to be people. In this example, we're looking at fast food restaurants, but x is the number of sample elements, let's put it that way, that have that characteristic that we're looking for, and then n is the sample size. So that's our population sample proportion. It's our estimate of the population proportion. And then, of course, we have to specify whatever confidence level we're looking for. Once we do all that, the calculator comes back with the numbers very quickly and easily. Now, there's one more case that we haven't considered yet. What if we're not interested in estimating the proportion for a single population, but what if we're interested in finding out if two different populations have the same proportion? Well, that's a very different situation. Just as an example, imagine if the, let's say that the government wants to know if the proportion of people who are retired is the same in New York and in New Jersey. That's the kind of situation we would use for what's coming up next, where we're constructing a confidence interval for the difference in two proportions. Okay, so now the test statistic, the formula is going to be a little bit messier in this case because we have two samples drawn from two different populations. And we need to specify one of them will be number one, of course, and one of them will be number two. It doesn't look radically different from what we've just been doing, does it? It's just a little messier because now we have to deal with two samples. So this is our point estimate. Okay, this is our z-score. This expression in the square roots is referred to as the standard error. Of P1 minus P2. And then this whole thing is the margin of error. And as usual, we're taking our point estimate and adding and subtracting our margin of error to come up with our confidence interval. And as usual, we will do this for three levels of confidence, 90, 95, and 99. Now, you already have these z-scores practically memorized by now, I think. Let me just quickly remind you, and I'm sure you'll agree that you're starting to remember these now. For 90%, z alpha over 2 is 1.645. For 95%, z alpha over 2 is 1.96. And 99%, we're looking at 2.576. All right. So by now, you know, they're starting to look very familiar, but if you forget, you can always look them up on the calculator or in the tables. Those are the three that you're going to need for the most part. All right, so let's do this. Now, there are two samples. The sample sizes will be called N1 and N2. Each one has its own X, and of course, that gives us two sample proportions. All right, so nothing's really changed. It's just, like I said, there's two instead of one sample. All right, now, suppose that a researcher wants to know if the proportion of people who are vegans is higher in California than in New York. A sample of 100 people is taken from each state. The number of vegans in the California sample is 10. And the number in the New York sample is 8. Okay, so what we need to do now is calculate a sample proportion for each state. And then we're going to compare them with our confidence interval. So now we're going to arbitrarily assign California to be state number 1 and New York to be state number 2. It doesn't make any difference which is which, as long as you're consistent. I only did it this way because California is alphabetically before New York. All right, I'm not making a value judgment here. I'm not saying, yeah, California is good, New York is bad. No, I just randomly picked California to be number 1 because of the alphabet, because it comes first in the alphabet. So let's summarize our data here. So in California, 10 out of 100 are vegans, which means the sample proportion is 0.10. And in New York, 8 out of 100 are vegans, which means the proportion in New York is 0.08. Now, they're pretty close to each other. So the confidence interval is essentially going to tell us essentially give us the range of possibilities, because we know that these are just estimates. We do not know the true population proportions. So we're going to plug these into our formula. Oh, but first, we'll remind ourselves, and we already knew this, and we've seen this before, that when you have 90% confidence, the z-score is 1.645. So you plug in these numbers, and this is what you're going to get. Okay, P1, remember, in California, it was 0.10. Therefore, 1 minus P is 0.9 divided by 100. In New York, it was 8%, which are vegans. Then we have 1 minus that is 92%. Finally, we have 100 in the denominator. Now, over here, you notice we're looking at the difference between the two. So at the moment, it appears if we just looked at these two, you would conclude that the proportion in California is 2% higher than in New York State. But we do know that there's a lot of uncertainty associated with this estimate. So that's why we construct this confidence interval to give us more information. Oh, God. All these ads. I'm always overwhelmed by all these ads. Okay. So let's see what that turns into. So it's 0.02. Now, the entire expression under the square root sign is approximately equal to 0.0404. So we've got 0.02 is our point estimate. And this is our margin of error. Now you notice the margin of error is actually larger than the point estimate. That indicates that there's a lot of uncertainty associated with this estimate. So the range, the actual range here is between negative. Now negative here means that New York is higher than California. In fact, about 4.65% higher. So yes, this number can be negative because it refers to the difference between the two. So this can be interpreted as New York is 4.65% higher. And this can be interpreted to mean that California is 8.65% lower, higher. And it could be anywhere in between. So that's a very wide range of possibilities, and that is useful information. Okay, it means that there's a lot of uncertainty. Usually what it means is that if we chose another sample, we might get significantly different results. So that means that from one sample to the next, there's a great deal of change. That's partially, I think, because the percentage of vegans is so small that it can be very different from one sample to the next. All right, now for 95%, the only thing that changes is the z-score, which of course increases the size of our margin of error. So here's the only difference right here. And that's going to make this entire expression, because remember before it was 1.645. So this margin of error will get even bigger. The interval will therefore become even wider. So let's see how big it gets now. Wow. So yeah, the margin of error is almost 8% now. It's almost 4 times as large as the actual point estimate. So you can see the range of possibilities is quite wide. So that means that we really shouldn't put a whole lot of stock in this result. It's most likely what we would probably do then, if we got these kinds of results, we would probably go out and try larger samples, because that is not a lot of useful information there. If I were a researcher, I would not publish these results, that's for sure. Because it's not telling me a lot, except that the samples are very different from each other. All right, and of course we want to try 99%, and now the interval will be enormous. The z-score jumps up to 2.576, and as a result, the margin of error will be enormous. The whole thing is the margin of error, of course. And now the interval will be, wow, look at that. The standard error is actually, the margin of error is actually 5 times as large as the sample, the point estimate. That's a lot. That's a lot of uncertainty. And so the result is that we have this enormously wide confidence interval, which the data tells us, this is what it is, but as far as practical usefulness, this is not terribly helpful. Now, of course, as you can probably imagine, there is a shortcut we can use on our calculators. So if you go to the same menu we had before, which is stat tests, you'll find it. Now, again, remember, we're only going to use the standard normal or Z interval when we're dealing with proportions. So all you have to know is whether or not you're looking at one proportion or two. So if you look carefully, you'll see in the menu, oh, here we go, 2 prop Z interval. Before, the other one said 1 prop. This one is 2, because it means that we're comparing 2 proportions to each other. Then you'll have to supply it with the X and N for both samples, as well as the confidence level. Not hard at all. So then when you throw in the numbers, you'll of course get the same results, more or less. There could be some slight rounding differences, as always. And so here, yeah, oh, okay, I didn't show it separately, but this is how you would get those same results. Okay, so now we're all set. So you've got several different kinds of confidence intervals in here. You've got confidence intervals for the population mean, with 2 special cases, one where we know sigma, one where we do not. We know how to do a confidence interval for a single population proportion and for 2 population proportions. Now, of course, there are more that we could do, but that has to wait for a more advanced course. Now, I know you're all itching to get into the next semester of statistics. I don't think they offer it at Purchase, though. You may have to wait till graduate school for that, but at least you have the most important ones down. All right, so now it's time for the last chapter of the course, number 10, which is our discussion about what we're going to call hypothesis testing. Oh my God. Wow, this is interesting. Doesn't it feel like we just started this course like 3 days ago? It's kind of hard to believe that we're almost done. Yes, it does. It seems like we just got started, and all of a sudden it's almost time to stop. It's kind of like a movie, a really good movie. When it ends, you're like, oh my God, that was so fast. I can't believe that was 2 hours. It's kind of like the same thing here. So I don't know, I guess that's a good sign that it feels like it went by quickly. All right, anyway, so hypothesis testing is just another approach to drawing conclusions about a population from samples. Now, the reason why all these different techniques exist is because each one is useful under different circumstances. Okay, in other words, for certain applications, hypothesis testing is the best approach to understanding what's going on in our population. For other scenarios, a confidence interval is probably what you really need. it depends on what you're trying to find out about your data. But ultimately, these last two chapters are very closely related to each other. And we'll discuss that more as we go along. It's almost like there are two equivalent ways of doing the exact same thing. Two sides of the same coin, I guess you could say. Now, here's a chapter where we do have to memorize a few key terms. Now, I did mention in the beginning of the course that we try to avoid having too many terms that you have to memorize, but every discipline has its own unique language, and we really just have to sort of get used to that. And so here we're going to introduce some very important ideas. I'm going to show you a list of the 6 steps that we follow every time we carry out a hypothesis test. So we'll go through them and explain them one at a time. So let me show you the list. And don't panic when you see it. It's long and there's a lot of details here. But once we've done this a few times, you'll realize that it's just a procedure. You don't really have to learn a lot of terminology, except in the beginning, you have to understand where we're going with this. All right, here we go. Oh my God, oh, look at all those details. So this is the procedure we will follow. So I'll give you a few minutes to make a note of this. And then we'll carry on. Okay. By the way, while you're looking at this, I just want to mention you have seen this word hypothesis before. Most likely it was in a high school science class like biology or physics or chemistry or whatever the case may be. The idea is very similar here. So I'll give you a minute and then we'll carry on. Okay. If I had music to play, I guess I would, but I don't. Maybe I could go find the Jeopardy song on the internet. No. All right. So you'll notice the first 2 steps involve hypotheses. There's 2 different hypotheses that we must specify when we run one of these tests. The level of significance, as it turns out, is very closely related to the level of confidence from the previous chapter. Then the next 2 are pretty much brand new. And then the decision rule just as a result of steps 4 and 5. Basically, 4 and 5 determine the result in part 6. It's not really a separate step as such. All right, are we all ready to go on? All right. So I just want to take a quick detour here. The last time you saw the word hypothesis, let's say it was in 10th grade chemistry. What exactly is a hypothesis when it comes to science? A hypothesis is basically just an idea that we want to test. So, for example, I might say in a different discipline, this might be my hypothesis. If I mix 2 chemicals together, I expect them to explode. So my hypothesis is that the combination of these 2 chemicals is volatile, let's put it that way. So how do I find out if my hypothesis is true or not? I do an experiment. This hypothesis can be proven or disproven by conducting an experiment. Now, in the hard sciences like this, and the soft ones too, I mean, if you're thinking about psychology, for example, It is possible to conduct experiments to carry out or find out if these statements are true. You don't have that luxury in other disciplines like economics and finance. In other words, suppose I had the hypothesis an increase in the money supply by 10% will increase inflation by 2%. How would I carry out an experiment to see if this is true or not? The problem is that the Fed can increase the money supply by 10%, but then a lot of other things will change at the same time. And I won't ever really know if my increase in the money supply was actually responsible for the corresponding change in inflation. So with a discipline like economics or finance, you have to take everything from the data that you have. In other words, you have to draw conclusions from your existing data. You do not have the luxury of carrying out experiments. So that's when this becomes especially important. How do we know what's actually happening with our data? Well, we have to carefully design a hypothesis test to draw the proper conclusions from the information that we do have. So here, for example, you would look at historical cases in which the money supply has changed, and then you would look at the corresponding changes in inflation and try to draw some conclusions about what you're seeing. So here, the hypothesis, the so-called null hypothesis, is the starting point. This is a statement that we will assume is true unless there is strong contrary evidence. In other words, we're assuming that this is true, and we're going to use our statistical data to determine if we can reject that null hypothesis, but only if we have strong, the magic word there is strong, contrary evidence. Now, in our case, we're going to focus our attention on hypotheses about the population mean, but you could also use the population variance or the population standard deviation. Actually, we're also going to do the population proportion as well. So in other words, we're not going to test whether or not two chemicals will explode. We're going to find out if, for example, the mean age in the entire United States is 30 years old. That would be a classic example of a null hypothesis. The government might say, listen, we have reason to believe that the average age is 30. We're going to assume that that's true unless our data tell us otherwise. Now, you saw in the list, we also need to have an alternative hypothesis. Oh, by the way, here's a good example, which has nothing to do with economics. The alternative hypothesis is what you accept in place of the null hypothesis if you discover that the null is false. A jury trial. Now, everybody's familiar with jury trials. You've seen enough TV shows during your lifetime to know how a jury works. Okay, somebody who's accused of committing a crime is brought in front of the trial, and the trial is held, and the jurors have to decide if this individual is guilty or not. You're told, though, and they make it very clear to you, and I've been in this experience, in this position myself, that you must assume that the defendant is innocent unless you have enough evidence to show that he's not innocent, and in which case you then declare that he is or she is guilty. So in that case, the null is innocent because we want to assume that unless we have strong contradictory evidence, like pictures of this person committing the crime. You know, that is what we would define as strong contradictory evidence. And therefore, we would conclude that the null hypothesis is false. The alternative hypothesis is true. And then we would convict this individual. But if we don't have enough evidence, then we let them walk. Okay. And so probably a lot of guilty people have gotten away with it because there was just simply not enough evidence to show that they were guilty. So the trials are structured to make sure that it's hard to convict people. You want to make sure that if somebody is convicted, that they're really guilty. And here, where we're not going to be looking at anything like this, we're going to be looking at population measures. So the null hypothesis is written in a very specific way. So let's say, for example, this H with a little zero next to it means that this is, in fact, our null hypothesis. So H0, the zero, by the way, the word null actually means zero. You hear that more often in British English, but null actually means zero. That's why we call it the null hypothesis. It's the starting point. So for our first few examples, we're going to look at the population mean, whose value we do not know, and we're going to assume that it equals this number. This is a constant. We will specify this constant in the problem. For example, remember I said before, if the government thinks that the average age in the US is 30, their null hypothesis would be written like this. They'd say, all right, well, we're pretty sure it's 30. We're going to look at our data and see if that's not true or not. Okay, so this is some constant. The little zero means that this is the value specified in the null hypothesis. It's written, this is a general expression, but you'll be given a specific number in the problems that you will be working on. Okay. What about the alternative hypothesis? How is that written? Well, there's actually 3 different ways we could write the alternative hypothesis, and this is something that we have to decide based on the problem. What are we trying to prove or disprove in this problem? Okay, so logically, if the mean is not 30, it's either above 30 or it's below. But we're going to allow for the third possibility as well, which is that the mean is simply different than 30. Okay, so let's see how that's written. So the alternative is the one, this is the hypothesis that we accept in place of the null if there is enough evidence to reject the null. Like, again, with the trial, if we have a lot of hard evidence that this individual did commit the crime, then we will reject the null and we will convict this person. So the names we'll assign to the 3 possible alternative hypotheses, these will not make any sense until you see them. But there's 3 possibilities. We're going to call the first one a two-tail test. The second one is a right-tail test, and the third is a left-tail test. You'll see why they have these names in a minute. Okay. So these are the 3 alternatives that we choose. We choose one of these to be the alternative hypothesis, and we'll choose the one based on what we're trying to prove or disprove. Okay, so in other words, this is our decision. As researchers, we're trying to figure something out, and we need to specify what the alternative is should we reject the null hypothesis. And again, if this is already sounding a bit overwhelming, once we do a few of these, you'll realize it's a pretty straightforward process. It just takes time to get used to this way it's set up and some of this terminology. All right, so let's see what these are all about. Now, wait a minute, it's starting to make sense here. So a two-tailed test refers to the decision to set this as our alternative hypothesis. Remember, the null is that mu equals some specific value. So in the first case, we're just saying if we reject this null, our conclusion is that the mean is simply different than this number. And that is a case where we don't really care if the mean is above or below this number. All we need to know is yes or no, are they equal? But if we need to know if the mean is greater than that value, that would be this case. Let's say the government is doing this test, and again, here's our example. They're assuming that the mean is is equal to 30. Why do they care anyway, by the way? Because they're thinking that let's say if the mean is above 30, then they may have to do something about the Social Security system, maybe because they're always worried that it's going to run out of money. And if the population is aging, then that increases the likelihood of that happening. So in a case like that, they might choose the right tail test because they really need to know if the population is older than 30. That's important. Now, on the other hand, if there's some reason why we must know if the mean is actually less than this value, that's the important result that we're looking for, then we'll use the so-called left-tailed test. In other words, let's say that the opposite problem occurs if the mean is under 30, then the government realizes, oh no, we need to build more schools. Well, we better get on that right away. So it's possible. It depends on what they're trying to find out, which one they will choose. In each case, when we get to it, it should be clear from the way the problem is written, which is the appropriate choice. All right, but any one of these could be used. And again, it totally depends on what information we're looking for. All right. So far, again, it is still pretty abstract, but it will be less abstract when we start doing our first example. Now, what comes next? What is the third step in this list? Level of significance. Now, this is something you already have been introduced to, but you did not realize it at the time. Let me jump ahead and show that one to you. The level of significance is alpha. Now, wait a minute. Didn't we just see alpha yesterday? Yes, we did. Remember, 1 minus alpha times 100 is defined as the confidence level. So that if alpha is 0.05, that implies that we're looking for a 95% confidence level. So the alpha itself has its own name. It is referred to as the level of significance. But here it has a very specific interpretation. Okay, so this means we have to take a bit of a detour right now. And we're going to introduce a couple of new ideas here. Suppose we're running a hypothesis test. What are the 4 things that can happen? Okay, I'm going to show you a chart which summarizes all the 4 possible outcomes of conducting a hypothesis test. All right, here we go. Now, let's say that the null hypothesis is true. If you reject it, you have committed what is called in statistics a type 1 error. If you don't reject the null, you've made the correct decision, of course. On the other hand, if the null is false, rejecting the null means you've made the correct decision, and not rejecting means you've made what's called a type 2 error. Now, I don't know where those names come from. You think they could have done something more original than that, but this is what they're called. All right, these are their proper names. So you can see, again, there's only 4 things that can happen: 2 correct decisions, 2 errors. All right, so I'll give you a minute to write that down. All right, so are we ready? So with all that being said, the alpha, the level of significance, can be interpreted as the probability of committing a type 1 error. Okay, so in other words, this is actually a decision that the researcher has to make, what level of significance to choose, knowing that that represents the probability of committing a type 1 error. Now, we cannot ever completely eliminate this as a possibility. There's always a chance of doing this, but we can control the percentage or the likelihood of it actually happening. by choosing a level of significance. Now, the majority of the time, at least in business, you'll end up seeing 5%. This is the most common choice, which also, again, remember, this corresponds to a 95% confidence level. So this is a popular choice in business. It seems to work well. There's no theoretical reason why we should use 5%, but it does seem to work very well. And so most researchers use 5%, but you can always use the others as well. It depends on how important it is, let's just say, to avoid a type 1 error. Okay, now, with all that being said, let's go back to this jury trial. Now, remember, the null is that this person is innocent. The alternative is that they're guilty. A type 1 error would mean that you've convicted an innocent person. Why? Because you rejected the null, that they're innocent. Now, if they really are innocent and you reject this null, that means you've convicted somebody who actually was innocent in the first place. But here, we fail to reject that null, which means we've let a guilty person get away. All right. Now, I think you'll all agree, though. Let's say we did choose alpha to be 0.05, that it's good to have a very low type 1 error probability in this example, even if it means a higher type 2 error, because as it turns out, the lower we set the probability of this type 1 error, the higher is the probability of the type 2 error. In other words, think about it this way: the harder it is to convict somebody, the more guilty people will get away. So there's a trade-off there. You want to make it difficult to convict somebody, but not impossible. So you have to find the right balance between the two. And that's what this alpha is all about, finding the balance between a type 1 error and a type 2 error. Now, imagine if this is medicine. We're doing trials on a new drug. Then in that case, it might be super important, like life-savingly important, to avoid type 1 errors. And that means that you'll set the alpha very, very low. Now, of course, in business, we're not ever really facing life-threatening situations. So 0.05 does seem to work very well. But in a discipline like medicine, you might find much lower levels of alpha. Let's say the null is that the drug is ineffective, and the alternative is that it is. You want to have hard proof that a drug works before you start actually using it. Okay. So now, oh, by the way, we do see, remember, alpha is the probability of a type 1 error. We also designate the probability of a type 2 error with the Greek letter beta. Now, it would be nice if these two add up to 1. They do not. The relationship between alpha and beta is actually very complex. We will not be calculating beta in this class, but the two of them do not necessarily add up to 1. Okay, now also we have this concept of power. This is the probability of rejecting the null when it's actually false. In other words, making the correct decision. In fact, you know what we could do here? Let me go back and get my chart. I like this idea. Hold on a second. This chart, what we can do is add some of these terms to it. So the type 1 error, hold on one second. I need a little space in here. Whoops. Nope, sorry. 1 minus beta. Power. This one doesn't seem to have a name. It technically, you can see it would have to be 1 minus alpha, but it doesn't seem to have a name. So we'll stick with these. Alpha for the reject type 1 error, beta for the type 2 error, and then the power is the likelihood that you will reject the null when it's actually false. Okay. So this way we can see them all together in one place and start to make sense out of it. All right. Oh man, it's just getting more intense, isn't it? Yes, it is. Now, before we go any further, I skipped over an example. I wanted you to just quickly see this. As far as the alternative tests are concerned, the alternative hypothesis, here's a scenario where the government of a small country is interested in studying household incomes in that country. And they need to know if the mean is greater than $25,000 per year. Let's just say that they're thinking about raising taxes, but they're not going to do it unless the income is higher than $25,000. If it's less, then they won't do anything. So the way they would write this test is the null would be that the mean is 25,000. And the alternative is that it would be greater than 25,000. Now we chose this one because we are looking for evidence that the mean is greater than $25,000. Okay. Now, by the way, I do want to point out some books actually do write less than or equal to here. This implicitly includes everything else. So in other words, some textbooks write it like this. Others just use the equality with the understanding that it includes everything that is not in the alternative hypothesis. So we'll stick with that convention, equal or something different. So this is an example of how you would choose the alternative hypothesis. We chose the right tail test because we're looking for evidence that the mean is above 25,000. Some action that we are thinking about taking depends on whether or not the mean is above 25,000. Very good. All right, so how many of these items have we covered so far? 3, null hypothesis, alternative hypothesis, level of significance. The test statistic is what's going to help us determine if we should reject the null hypothesis or not. Okay, so we'll see how that works down here. The test statistic is a numerical measure that is constructed to determine whether or not the null hypothesis should be rejected. Now, if we're using a population mean as we are here, the test statistic depends on the sample size and on whether or not we have our population standard deviation. Okay, now, as far as the sample size is concerned, you might remember that when we looked at the central limit theorem, way back, whatever, chapter 8 that was, a small sample is defined as n less than 30. A large sample is 30 or more. And in general, we use the t distribution for the small samples And in general, not always, there are exceptions, but the standard normal is usually reserved for cases where we have large samples. And that's because the sample mean can be very different from one sample to the next when we have a small sample. And so we need the t-distribution to reflect the greater variability from one sample mean to the next. Because remember, the t is more spread out than the z. In fact, this is why Gossett invented this distribution for these very cases, small samples. All right, so this is z, and this is t. And they both, of course, have a mean of 0. Very good. So if we have a small sample, this is going to be our test statistic. All right, are we ready? It's not, when you say it, you won't pass out. It's not that hard. Okay, oh my God, look at this. Well, the only thing that's mysterious and new, this is the hypothesized value of the mean, of the population mean. Remember, in the null, the general expression is this. That's this. Of course, x bar is our sample mean. Our old friend x bar is coming back. S is our sample standard deviation. And of course, n is our sample size. And t represents the t-distribution, of course. So all of that will give us a single number, which will help us determine if we should reject the null or not. The larger this number, the more likely we are to reject the null. Okay, so you'll see that as we go along. Okay. And all right, now, what about the other cases? Well, as I said earlier, if the sample is sufficiently large, the normal practice is to use the standard normal distribution. All right, so the actual form of this test statistic will not change. Okay, let me show you what I mean. By the way, this is just a point of terminology. This denominator is often referred to as the standard. Now, you don't have to memorize this, error of x bar. It basically refers to how much different each sample mean is likely to be. Okay. All right, other than that, I think we're good with this. What if the population, now here we have two possible cases. We have large sample. Oh God. But there's two possibilities. Sigma is known and sigma is unknown. But in either case, use the standard normal distribution. Now, if you look at it carefully, this is the same thing we just saw before, except we have sigma now and we have z. So the actual calculations are no different. And of course, this is our old friend, the standard normal distribution. This is so you can see from this formula, what you're actually doing is creating what's called a z-score. You're going to find yourself somewhere along this normal curve. Let's say that this turns out to be 2, then you'd be up here somewhere. Okay, so what the test statistic is actually doing is showing you a point under the standard normal curve. That's all it is. Now, if it's very far away from the mean, that would indicate that the null hypothesis is unlikely to be true. So again, larger z means the null is less likely to be true. And then the second case where sigma is unknown, but we still have a large sample, we're only going to make one subtle change. We're going to replace sigma with s. It's just that simple. All right, let's show. Yep, there it is. You see what I mean? The only thing that changed here is that we have s instead of our original sigma. Otherwise, it is exactly the same. All right, now, once we have our test statistic, let's say that this, like I said, let's say this turns out to be 2. The question is this, what does this tell us? Does this mean that we should reject the null or not? We have to have something to compare this with before we make our decision. In other words, is this too far away from the mean? Now, if the null hypothesis is exactly true, in other words, let's say the null is that the mean is 10. If the population mean really is 10, then the test statistic should be right here at 0. The fact that it's at 2 means that the null might not be true. But are we far enough away to conclude that the null hypothesis is false? Like, here's an example. Remember, we talked about the null hypothesis that the mean age of the United States is 30. What if I come up with a sample mean of 33 and my test statistic is 2.17? Does that give us enough evidence to suggest that we should reject the null hypothesis? And the answer is we don't know until we construct a benchmark that we can compare these with. And that benchmark has its own special name, of course it does, called a critical value. Now, I've used this analogy in the classes before, and maybe this will make sense to you, maybe it won't. The best analogy I can think of is the foul pole in baseball. Well, what does that have to do with anything? The foul poles. These determined, or they show you the limit to how far the ball can go and still be fair. And so a critical value tells you how far we can get away from this mean of 0 without rejecting the null hypothesis. In other words, if you can imagine, let's say this is my critical value. That means I do not reject the null because z is not far enough away from the mean. But if the critical value was down here somewhere, that would mean we reject the null. So don't worry, we'll go over this again multiple times, but just think of it as the benchmark. Or it's like right here, up to this point, we failed to reject the null. It's fine. The null is fine. Anything out here in this range, then we're simply too far away from the mean to accept the null hypothesis. So the critical value is the sort of like the dividing line between rejecting and not rejecting the null hypothesis. In fact, why don't I draw another little picture here so you can see this a little better. And let's say this is our critical value. Anything in this range means we reject the null hypothesis. And it works in both directions too, by the way. We can have a negative critical value. And that means everything down here will tell us that we should reject the null because we're just too far away from the mean to be consistent with the null hypothesis. So doesn't that remind you the foul poles in baseball? These are the two foul poles and the rest is fair territory. Maybe not. But anything in these two tails would cause us to reject the null hypothesis. So if the test statistic is too extreme, which means too large or too small, we reject the null hypothesis. And this is how we can tell by looking at this critical value. All right. All right. Now, and again, I know this is a lot to take in. Believe me, once you've seen a few examples, it'll all fall into place. But it is, oh my God, it's already after 11. So why don't we stop here for a few minutes to recuperate, and then we'll pick it up. I'll show you what the critical values are, and then we'll do some examples from start to finish, and then we'll see how this all actually works. Okay, all right, let's do it. All right, so we're ready to look at critical values. All right, so the critical values depend on, they're going to come from either the normal, standard normal, or the t-distribution. So the way it works is that if you have a large sample, you're going to use the standard normal distribution for your critical values. Now, the critical values themselves depend on which alternative test you're using, or alternative hypothesis you're using. So the two-tailed test uses two critical values, plus and minus z alpha over 2. This is exactly what we saw with the confidence intervals yesterday. We didn't call them critical values, but that's what they're known as. In other words, remember we had x bar plus and minus z alpha over 2, this kind of thing. This, it's a z-score. In this context, it's referred to as a critical value. All right, so z alpha over 2 means you're looking at two z-scores. Okay, so that means if your test statistic lands in either of these two shaded regions, you're going to reject the null hypothesis. On the other hand, if you're only conducting a right-tailed test, let's say you're only interested in whether or not the mean is above a certain value, then you only need one critical value. So let's see if I can squeeze that in here. So that would look something like this. So in other words, anything in this shaded region, in that case, would be lead us to reject the null hypothesis. If you have a left-tailed test, then you only need one critical value, which is in the left tail. Okay, you get the idea? That's where the name actually comes from. If you think of the shaded regions as tails, you can see the origin of these names now. This is the two-tailed test, and the two-tailed simply means this shaded region, which is also known as the rejection region, has two tails. Oops, what did I do? Rejection, right. Rejection region. Okay, is these two tails. All right, down here with the right tail case, the rejection region is the right tail. With the left tail case, the rejection region is the left tail. All right, so now that those names start to make sense, don't they? The two-tail, right tail, two-tail test, left tail, specifically refer to where the rejection region is located. Now, we can figure these out with our calculators without too much difficulty. The alpha in these cases actually refers to the area in these tails. So here you have alpha over 2, alpha over 2. Here you have an area of alpha, and here you have an area of alpha. Okay, now we're going to practice looking these up, by the way. So yeah, like I threw in an example here. What if we chose our alpha to be 0.05, which again is the most common choice? And we have a right tail test. All right, so imagine we decided that we have a right tail test, and now this is the standard normal distribution, so the mean is 0. This z alpha value, whatever it is such that the area in the right tail is 5%. And of course, that means everything below it is 95%. How do you find this on your calculator? Well, one way is to say, all right, well, let's go to second VARS, choose INV norm, and what you're going to do is enter INV norm. Not of 5%, but of 0.95. Okay, because remember that this is geared towards everything below that point. And when you do that, you'll discover a familiar number here, 1.645. Okay, so this is critical value, as it's called, is 1.645. Now, we can interpret that as being 1.645 standard deviations above the mean. Anything beyond that is too far away from the mean to be consistent with the null hypothesis, and that means we should reject it. All right, so let's say that, just as an example, if our test statistic is greater than 1.645, we reject the null. Otherwise, we do not.
So I have a quick question, Professor Anderson.
Yes, go ahead.
On my calculator, when I go to second var,
Yes.
I select the tail and I get a positive value, but if I select the right tail, I get a negative value.
That's how it should work. Because of the symmetry of the distribution, if you put into your calculator INV norm of 0.05, you should get negative 1.645. Okay, so in other words, and again, I'm desperately short on space here, but 1.645 up here has a right tail of 0.05. Down here at negative 1.645, we have a left tail of 0.05. So if we had a left tail test here, then you would have chosen the negative 1.645.
Okay.
Right, so if it's a right tail test, we use this one. If it's a left tail test, we use this one.
Got it, thank you.
Okay, now, of course, if it's a two-tail test, oh, and then this is just what, if you looked it up in the chart, we did this before, it's halfway between 1.64 and 1.65. In other words, if you need to do this with the chart, you would be looking for the 0.95, not in your calculator, but in the body of the table or chart. And in this case, it happens to be halfway between these two values, which means it's halfway between 1.64 and 1.65, which we normally just round to 1.645. That's standard practice in statistics. For this particular case, oh, I did draw a picture of it. Okay. The left tail version, because of the symmetry of the distribution, as I just said, would be negative 1.645. And then, of course, if I have a two-tail test, that 5% has to be split up between the two tails. They won't each have 5%. They'll each have 2.5% of the total. And that's going to give me 1.96. How do you know? Because if you go to INV norm of 0.975, in other words, everything from this point down adds up to 0.975, you will in fact get your 1.96. If you do INV norm of 0.025, it's negative 1.96, again, because of the symmetry of the distribution. So those are the critical values. And again, that's the dividing line between rejecting and not rejecting the null. So here, you would reject the null if your test statistic is in either of these two tails. It doesn't matter which one. Again, you can think of it if you want to as foul territory in baseball. Okay. It goes outside here. We reject the null. That is a home run. How about that? All right. Now, all of that was for the standard normal. Now, remember, this happens when we have a large sample. We're going to have to do, unfortunately, the same thing for the t-distribution as well. The complicating factor here is that we also need to specify degrees of freedom to look up these values. Luckily, it's easy to calculate degrees of freedom in this application. That will always simply equal n minus 1, the sample size minus 1. So you see, that's why they're written this way. Now, these are also, even though they're based on the t-distribution, they're also still referred to as critical values. Although you could call them t-scores if you want to. They're in this application, they're called critical values. And the logic is the same. The two-tailed test has two values. Right-tailed test has a positive value. Left-tailed test has a negative value. All right, so let's see an example of this. Let's just say that we have a sample size of 20 and a level of significance of 5%. So then we have a single critical value. And if we find our test statistic in this region, we reject the null. And also we note that the area in here equals 0.05. The remaining 95% is down here. Now, we can look this up in our tables. I think I have an example of it right here, yes. So with 5% in the right tail and 19 degrees of freedom, the critical value is 1.729. But if you're going to use your calculator, the function you need now is not INV norm, but INVT. Now, when you come up with INVT, it's going to ask you for the area and the degrees of freedom. Now, when it says area, what it actually means is everything below that point that you're looking for. So here, that would be 0.95. So this is geared towards less than or equal to, just like the standard normal. And we have 19 degrees of freedom because the sample size is 20. All right, so let's throw those in and let's see what it comes up with. Oh, wait a minute, I did something wrong, never mind. .95 and 19. Okay, 1.729, that's it. All right, so you've got those two choices to look up your critical values. Now, if we had a left-tailed test, then this would just be negative. Okay, so that's easy. Let's see. Oh, yeah, here we go. Here's the right-tailed test. And here's the left-tailed test. And you would find this as INVT. Area is 0.05. Degrees of freedom is 19. And then if you plug in those numbers, you'll get negative 1.729. And then, of course, with the two-tailed test, the 5% is split up between the two tails. Each one will have an area of 2.5% instead of 5%. Okay. Just like with the standard normal distribution. All right, how would that work? So notice again, when you divide alpha in half, each tail now has 2.5% in the worth of area. And if you go to the chart, you have to move over one column. This is the one tail. And 19 degrees of freedom gives us a value of 2.093. And that means right there. So you've got both plus and minus 2.093. You can certainly find this with your INVT function. So here, what we can do is, remember, this gives me a total area below it of 975. And degrees of freedom is 19. It should give you a roughly 2093. If you change this to 0.025, that's going to give you the negative of this. Okay, so you don't have to actually do this twice, because once you get this 2.093, it should be clear that the negative version would just, you just make this negative for the lower tail, because the t distribution is symmetrical, just as is the standard normal. All right, well, now that was a lot too. You can see now the decision rule, I think we already understand this very well. Basically, what it comes down to is if the test statistic lands in the rejection region, then you reject the null. That's why it's called the rejection region. So this is what we mean by the decision rule. Okay, so with any right-tailed test, we have a single critical value, whether it's based on the t or the z. I'll just call this critical value. And this is what we will call our rejection region. With the left-tailed test, I'm working on I still didn't get a chance to get back to everybody about receiving their problem sets and their midterms. I'll take care of that later on today. I probably did, but I'll let you know. All right, with the equivalent left-tailed test, this would be our rejection region. And you've noticed the thing that these all have in common is that if the test statistic is what we call more extreme than the critical value, that's when we reject the null. All right, and then finally, and by the let me add one more detail here. This area has a total. This is has a total area of alpha. Okay, same thing with the left-tailed test. The area equals alpha. And then the two-tailed test, the difference here is that we split it up. We have two critical values. They're the same number, but one is positive and one is negative. But the area in each case is alpha over 2. And so this is the other half of the rejection region. And the area is alpha over 2. All right, so in general, this is how the decision rule works. Okay, now everything is done. All the background is in place. We can finally do an example, all right, from start to finish. And when it's over, you're going to say, well, you know what? That isn't nearly as complicated as it looks. All right, so here's an example. Using the example of the government of a small country, which we briefly looked at earlier, the government wishes to know if the mean household income is greater than $25,000 per year. Fine. So they choose a sample of 100 households. The mean household income in that sample is 27,200. So in other words, N is 100 and X bar is 27,200. And the sample standard deviation is 8,400. But since the sample size is greater than 30 or equal to 30, we use the standard normal distribution for our test statistic and our critical values. So the first thing we need to do is set up the null and the alternative hypotheses based on the fact that we were told that the mean, what we want to know is if the mean is greater than $25,000. So that implies that we're going to set it up as a right-tailed test. Okay, greater than means a right-tailed test. All right, so what would that look like? Here we go. And yes, indeed, it is in fact a right-tailed test. All right, so the question is whether or not we have enough evidence to suggest that the mean is in fact greater than $25,000. Now, as usual, we'll choose alpha to be 0.05. That's a common choice in business applications. And of course, let's not forget that this refers to the probability of a type 1 error. Okay, well, that's not part of this process, but I just wanted you to remember this. So we've chosen alpha to be 0.05. Now, in any problems that you'll be given or on the exam, it'll tell you in the problem what to use for alpha. You will not be, you're not the one who has to choose this. It'll be built into the problem. Now, the next step is to calculate the test statistic. So what you need to do is make sure you pick the right one. And again, remember, we discussed this as Z is being used because the sample size is large. S is being used because we don't know the population standard deviation. So when we plug in these numbers, we're going to get our test statistic. All right, are you ready? So we plug them in and we end up with 2.62. Now that's a pretty large number. But we can't draw any conclusions from this until we know what the critical value is. Now, this is a right-tail test, so there will be a single positive critical value. But what is it? Okay, all right, let's recall that the critical value will be some z-score such that this mystery z-score, the area in the right tail is 5%. Okay, so what value does that correspond to? Well, again, we can look it up with our IMV norm function or go to the tables. And you'll recall, oh yeah, we've seen this one before. It's 1.645. So let's confirm that. Yep, 1.645. So this is what our diagram is going to look like. Look how nice that is. Here's our critical value. The shaded region is the rejection region. The area is alpha, or 0.05. But our test statistic is here, which means it's in the rejection region. So what does that tell us? We reject the null hypothesis that the mean is 25,000, and we accept the alternative that it is in fact greater than 25,000. Which means that let's say, remember before, we assume that if incomes are higher than that, then they may decide to raise taxes. Well, now they have enough evidence to suggest that the mean is in fact above 25,000, and they can go ahead and feel free to raise taxes because we have enough evidence. Now, you notice we didn't actually go to every single household and figure out what their incomes were. This was good enough, okay? Because we've set up the procedures correctly, we have hard evidence that the mean is greater than 25,000. Wow. Now, so you notice the actual process wasn't that bad, was it? We needed to start by specifying the null hypothesis and the alternative. We were given the level of significance. We calculated a test statistic. We look up the critical values in our chart or on our calculator, and we compare them. And that's all we have to do. So with all that background theory, it must have seemed like this was going to be a complete nightmare. Well, I would have to say that it isn't. If it is a nightmare, it's not a bad nightmare. Let's put it that way. It's a relatively pleasant nightmare. Okay. But so this is what's going on. We've just demonstrated that we have enough evidence to show that the mean is greater than 25,000. And we're done with this example. Wow. Oof. I can feel your exhaustion through the internet. That was a lot of detail. So then there's a second example here that we're going to go over. And then there's a few extra details at the end here. There's an alternative approach that we can take, which might be a little bit quicker. We'll look at that tomorrow. And then we'll go through it again. But then if time permits, I think that it's time. I'm going to put the sample final on the Moodle. I don't want to waste time. All right. If we finish early tomorrow, I would like to at least start to look at the sample final, just because it's bound to be very long. So that's what I think we should do tomorrow. Now, of course, we're going to go over this again in great detail tomorrow. We want to make sure we really learn this stuff. But if there's a little extra time, I think just because we're almost done with the course, we may as well get cracking on the sample final. Luckily, we do have 2 days left next week, but we don't want to get complacent, do we? No, that's never good. So we're going to finish this tomorrow. In fact, we'll take a step back and review everything we did. We'll go through the examples. I'll show you the alternative approach, and then I'll show you some calculator shortcuts. And then we'll probably have a little time left to at least start the sample final. All right, so I guess now there's nothing to do except rest for a while. And then what you should probably be doing is finishing up any assignments that are outstanding. And I will, as soon as I can, probably this afternoon, get you the problem sets for chapters 9 and 10, as well as the sample final. And then we'll be ready to roll tomorrow. All right. And also try, if you've got a few minutes, try to fill out the evaluations while you're thinking about it. I don't know how long it'll take. I'm sure it's pretty quick, but the more people who do it, the happier the school will be. And that's what we want. All right. So unless there's any last minute questions, I guess I'll just see you all tomorrow.
Thanks, Professor.
Okay. You're welcome. You're welcome.